we can archive the data better, we can link different data sets, we can, if we're going to collect more data, we can collect different kinds of data, such as discrete data sets, so we can collect more samples, do more geochemistry, more XRF data, or we can collect continuous data sets like digital photographs or hyperspectral imaging. We can choose a traditional technology that everybody's comfortable with. We can explore emerging technologies that are more risky. The problem is all of this costs money, and it takes time, and it takes a knowledge, a workforce that knows what they're doing. So when we start to explore different technologies to help us do a better job, there's something called the ideal technology checklist that I like to put up. First of all, if we're going to pick a new technology to identify rocks, it better be affordable, it better be safe. We can't be bringing extra people on site. It should have continuous data collection so that you're collecting data from all of the rocks, not a subset. It should fit in with the workflow. I don't like the idea of disruptive technology. I feel like technology should fit in like a missing piece of the puzzle, should produce high value results and complete integration with systems that already exist. So I'm showing this graph of the technology hype cycle because I think that it's important to know that when a new technology shows up, what we're going to experience as humans as we learn about that technology and start to use it. And one of the examples I like to use is the portable XRF, which I first saw about 10 years ago at a conference. And I remember everybody was talking about it. And it was the big thing. And that was, for me, the technology trigger for the portable XRF. After that, everybody was expecting it to solve all their problems. So you could do A, B, C, D, E, F, G, and it was going, silver bullet, it was gonna fix everything. So then you're in the peak of inflated expectations about what this technology can do for you. After a while, you realize those expectations weren't realized. You go down into the trough of disillusionment where you basically dislike the technology, you think it doesn't work, it didn't deliver on its promises. You feel perhaps a little betrayed by it. So then after a week or a month, you realize, wait a second, it actually did work for specific deposits. Didn't work on everything, but there were those case studies we did where it was great. And you're on the slope of enlightenment where you will recognize when that technology is appropriate to use and when it's appropriate to leave in the cupboard. And then once you have that settled, you've got your workflow sorted out, then you're on the plateau of productivity, where you can know when to pull out that technology and when to use it in combination with other techniques. And hyperspectral is on this cycle. So it is, for some people, they might be expecting it to solve their problems. They might be in the trough of disillusionment where they very much dislike it because it didn't work. And then for other people, they are just first hearing about it. Or perhaps you're on the plateau of productivity. But before we get to the MICAs, I want to explain what hyperspectral is, just for people who don't have a clear idea of what I'm talking about. So a normal camera, like the camera in your digital SLR or your smartphone, has 3 discrete data channels. One channel collects at red, one at green, one at blue. So each pixel in the picture has 3 data points that are represented over 3 data channels. More complicated systems are multispectral systems. So you have more than 3 data channels, and they can be discrete or they can be overlapping. And so this example shows 7 overlapping data channels. And this could be something from a UAV, a satellite, an airborne system. And then there's hyperspectral systems, which are more complicated. They can have hundreds to thousands of data channels that span the visible and then can even go into the near infrared and shortwave infrared as well. And so if you have all of these, so each pixel or each collection of each measurement will have 200, 500, 1,000, 2,000 data points. What you can do when you look at that data is you can connect those data points and you'll make a spectrum. And so we'll be talking about spectra going forward. But a little bit about the infrared. The shortwave infrared is a very important part of the spectrum. It is the wavelengths longer than what we see in the visible, and it provides information about composition, especially in regards to minerals and rocks. So it's very, very sensitive to the hydroxyl bonds, to water, carbonates, and sulfates. In the long wave infrared, you've got things that are more in the silicates and the carbonates range. So we'll be looking at the shortwave infrared when it comes to Olympic Dam and its MICAs. Reflectance spectroscopy is the foundation of hyperspectral analyses in geology. So when we collect hyperspectral data from minerals and rocks, we're looking at electromagnetic radiation reflected from the mineral or the rock. So we're not doing transmission, we're doing reflectance. And reflectance spectroscopy can be used to identify the presence of minerals. It can be used to determine their composition and then determine their abundance. And the way this happens is that the water molecule, for example, is what I'm showing here, has bonds in it between the hydrogen and the oxygen that absorb radiation at specific wavelengths. And so when radiation is shined onto the water, it will absorb that information, absorb that radiation, and there will be less of that radiation reflected back to the detector. And that causes a trough in the spectrum. And so if there are specific bonds in a mineral, they will absorb information, producing a trough in the spectrum. And we use these troughs to identify the presence, determine the composition, and determine the abundance of minerals. The advantage of using reflectance spectroscopy techniques is that little or no sample preparation is required. You don't need to cut the samples, you don't need to polish, and you don't need to grind. The samples do need to be clean and dry, however. Another advantage is it can be used in the field. And third, perhaps, is most people don't know, is these machines can work very, very quickly. And so, for example, it can take, with a traditional portable XRF, it takes about a minute, for example, to collect one measurement. A reflectance spectrometer that can be used for hyperspectral data analysis can collect one spectrum in 6 milliseconds. So you can collect 150 spectra per second. So therefore, you can mount it on a stage or an arm, and you can move it over the surface, and it will collect continuous full coverage data. And this is how satellites and airborne imaging systems work as well, as they work very fast to collect data. So on to the white micas, which is why we're here. So white micas, in reference to this particular talk, I'm going to be speaking about muscovite and phengite in particular. And the definition would be, on the right-hand side, you've got this ternary diagram that shows muscovite in the top triangle, and you've got something called the phengite series below. So if we look on the left, you have of the structural diagrams here, you've got muscovite having aluminum, silicon, oxygen, hydroxyl, and potassium. And phengite actually has substitution of the aluminum. So aluminum is getting removed, and you're getting additional silicon into the tetrahedral layers and iron and magnesium into the octahedral layers. The important thing to remember, though, is that the interlayer cation charge is still going to be between 0.85 and 1 cations, which are potassium. And this is important because as soon as we start lowering the amount of cations in the interlayer area, as you start getting into clay territory, and that's a different story, and then sericite and illite and clays is another set of diagrams. So we're talking real micas have a very nice chemical composition that could be obtained by microprobe, and that would fit somewhere on this ternary diagram on the right. The important thing to remember is these have hydroxyl and water in them as well, which is what we're going to be measuring when we start collecting spectra. So some of you are probably familiar with the 2200 nanometer band. So this is the white mica wavelength. So this is a particularly important and perhaps the most used and most examined trough that spectroscopy has right now when it comes to minerals and rocks. And this trough is produced by the combination of the hydroxyl stretch with the aluminum hydroxyl bending mode. And it's completely diagnostic for dioctahedral phyllosilicates. It's almost nearly impossible to get this trough in any other material. So when you see that, you know that you have a dioctahedral phyllosilicate. We can also use to distinguish between the phyllosilicates because troughs at shorter wavelengths relate to a higher aluminum content. And this is because we're actually measuring the aluminum hydroxyl bond. So more aluminum is at shorter wavelengths. Lower aluminum abundances are found at longer wavelengths. And also, if we have a deeper trough, that means we have a higher abundance of the mineral in total. So based on the spectroscopy, we can use the trough at 2200 nanometers to identify the presence of white micas, determine their composition, and determine their abundance. And this is very useful when you're looking at a ore deposit that likely has ore minerals in combination with some kind of phyllosilicate, a dioctahedral phyllosilicate, and most of them do. So Olympic Dam was formed by hydrothermal fluids that explosively brecciated country rocks and precipitated minerals. There's copper, gold, uranium, and rare earth elements found in hematite breccias. We've got rocks containing phengites that have been identified to be as barren. And then as you move away from the deposit, you actually have less phengite appearing. So the hematite breccias and the phengite-rich rocks are complexly intermingled, making visual inspection very difficult. And this is why automated systems are actually quite useful for, especially when looking at breccias. So the drill core that I analyzed was RU395371. And this is a pretty standard, drill core has been analyzed by a lot of people throughout time. I was at the University of Adelaide in 2007, I believe I started this project, 2006. And this drill core had already been scanned. It was using the HYLOGGER. So the HYLOGGER was at PERSA at the time, and Georgina Gordon, Alan Major, John Huntington, and David Giles all helped with this project, Kathy Eric as well. And the drill core itself is 300 meters long. The top 30 meters are ore-bearing hematite breccias. Then you have 170 meters of complexly intermingled hematite breccias with hematite-rich breccias and heterolithic breccias. And it's in these heterolithic breccias that we're going to see the MICAs. And there's a picture of them on the right-hand side here. Or actually, that's a picture of the ROXBY Downs granite, sorry. And then at 200 to 300, you've got the ROXBY Downs granite. And so the picture on the right-hand side here is the contact between the Olympic Dam deposit and the ROXBY Downs granite here. And that happens exactly right there. So the data set I was provided with contained two sets of HYLOGGER data from HYLOGGER 1 and HYLOGGER 2, and examined 220,000 spectra from 300 meters of drill core. I also collected microprobe data from 5 samples that had white micas, and then I was provided with the whole rock geochemistry. So here's a picture of the heterolithic breccia, and you can see that, and this is within the Olympic Dam ore body itself. So this is really near the top, is at between 30 and 35 meters. You have very rough looking rocks. They clearly don't have any ore in them, and they're different colors. They look pretty beat up here. Sorry. And here's a picture of the ROXBY Downs granite. So this also has a lot of white micas in it. And the question that I was asked to answer was, what are the difference between the white micas in the ore body and outside of the ore body? But first, of course, you have to look at the ore minerals at Olympic Dam, because why not, right? So here we have some reflected light microscopy. There's some hematite, chalcocite, and bornite, and then chalcopyrite placing pyrite with some hematite. And look at those pictures. There's lots to look at, but I just showed some here right now to see that there is some ore mineralogy pictures. But back to the white micas. So the white micas are not as exciting, obviously, to look at as the ore minerals, but here we have the physical appearance of the white micas within the heterolithic breccias, which are within the Olympic Dam ore body. You've got, it's a brecciated system, so you've got a lot of breakage here. And then if you look at the white micas in the ROXBY Downs granite, you can see visually that they are different. So great, so we know that they're different. Obviously, they wouldn't be the same things, but let's start to learn more about them. So the HYLOGGER data that I was provided with was an excellent data set, came with pictures, came with spectra, and I initially used TSG, the spectral geologist, to look at the data. And this is very, they work together, right? So TSG has this wonderful function where you can upload your data, and it has a spectral library of minerals, and it will start to unmix and tell you its idea of what minerals you have in your rocks based on the spectra you've provided. So if we really simplify the kind of parameters down at this first block here in this gray area with the yellow and the gray on the left, we can see that here we have the top 30 meters of the ore, and then you have the white micas coming in yellow, and chlorite and white mica in the bottom 100 meters of the ROXBY Downs granite. Okay, so great. The hyperspectral data is able to tell us, give us a first pass assessment of what's really happening. The problem is then when you go to look at the white micas and the composition of the white micas is that it is relying on a spectral library that was provided by an external data set, something that they collected from somewhere else. And so if you look at the and put the HYLOGGER Olympic Dam data into TSG, it then will tell you that the white micas at the top of the drill hole are muscovite and the white micas at the bottom of the drill hole are phengite, which is not true. It is known that the white micas at Olympic Dam are phengites. So why is the TSG telling us something different? And that's actually can be explained by doing by looking at this next slide. Here we go, where TSG always says, it says at the bottom here, very fine print, use with understanding and use at your own risk. So there is inherent risk in using an external spectral library to interpret your deposit, especially if you have a real ore deposit that has extremely complex mineral assemblages. So let's take a look at that white mica wavelength issue. So we've got, I took all of the white micas that were identified in the ore zone and compared them, identified their wavelength, white mica wavelength position. And then I went and took all the white micas I identified in the unbrecciated ROXBY Downs granite and identified their wavelength, white mica wavelength as well. And here's the histogram showing that. So in the brecciated ore zone, there's a large distribution of white mica wavelengths. And in the ROXBY Downs granites, we have a nice Gaussian curve centered at 2213. If we look at the brecciated ore zone, the average spectral position of the white mica wavelength is 2206, which is firmly within the muscovite. You know, that's where most people would put muscovite. So the white micas identified in brecciated ore-bearing zones are identified by TSG as being muscovite. And it wouldn't be just TSG. This would be any linear unmixing software would identify these minerals as being muscovite. But when you go down, when you have a different spectrum that shifts to 2213, the white micas identified in the unbrecciated ROXBY Downs granite are identified by TSG as being phengite. Well, let's look at the microprobe data. So that ternary diagram showing up again. And so what we have is when we plot, we have 5 samples that were collected from Olympic Dam that had white micas in them. After microprobing, it was found that the phengites from the ore zone plot in a different area than the phengites from the ROXBY Downs granites, but they're still not plotting as muscovite. They're all plotting in the phengite series. The only difference between them is that the white micas in the ore zone had contained more iron and more aluminum than the white micas identified in the ROXBY Downs granite. So here we have many microprobe data, none of them plotting the muscovite zone, muscovite top of that triangle. So how come we've got phengites making spectra that look like muscovites? And the truth is that all we have here is a high aluminum phengite that produces a spectrum that resembles muscovite, because what spectroscopy is doing is it's measuring specific bonds. And those bonds help us infer what mineral it is, but you can have very similar bonds, especially when it comes to aluminum hydroxyl. You can have similar bonds in phengite as you do in muscovite. The rest of the mineral might be different, but those particular bonds might resemble each other. And so here at Olympic Dam, we have high aluminum phengites in the brecciated ore-bearing zone, and we have low aluminum phengites in the ROXBY Downs granite. There are no muscovites in these samples, even though if you were to do linear unmixing with these spectra, you would have muscovite coming out as your primary mineral in the upper part of this drill core. Let's take a look at more microprobe data and some pictures. So here you can see all of the white micas plotted on a nice line there to make sure that the data are good. We've got high aluminum phengites in the top, low aluminum phengites in the ROXBY Downs granite, and that they're actually quite different populations that don't really overlap either in their compositions. They're quite different minerals, even though they're both phengites. So how do they look different? In the top picture here on the right, you see this phengite really looks like it's forming a lot of the picture. Whereas in the ROXBY Downs granite, the phengite is a sericite on the feldspar, sericitizing the feldspar. So not only do they look different, they produce different spectra, they produce different microprobe data. They're actually in thin section actually look quite different as well. So now that we know that the mineral we're looking at is phengite in the white micas of Olympic Dam, we can then go and start to quantify how much there is as we go down the drill core. And this is where the fun comes in. So here we have a red box. In that red box, there are two columns. You've got this dark color, which shows the intensity of the 2190 to 2230 nanometer spectral feature. So this is the white mica trough. So we're measuring the intensity of that trough, which will tell us how much phengite is there, regardless of the phengite's composition. So to quantify troughs between 2190 and 2230, you can use band ratios, you can do Hull quotient analyses, you can do second derivatives. There's a variety of ways of measuring that. The important thing is that you pick something that works for your data. And what you see here is when you plot the intensity of that trough, the white mica wavelength, against aluminum weight percent, which was derived from whole rock geochemistry, you see that there's a very good correlation between the two. So you have an independent data set validating what your spectroscopy is saying. So it takes a lot of effort to collect whole rock geochemistry, but here, and it's not continuous, it's perhaps maybe collected every 5 meters or every 2 meters, but with the hyperspectral data, you're collecting a measurement every centimeter when it comes to the HYLOGGER data. So because we know that phengites at Olympic Dam mean there's no ore, then this dark colored plot here shows where you have barren regions along the drill core. That's been independently verified with the whole rock geochemistry data. But we can also use another bit of information in the spectra to actually identify the iron oxide as well. So to identify the iron oxide, we're going to document the shift of the 900 meter trough, which captures the relative abundance of hematite, goethite, and surface oxidation such as lepidochrokite. So by measuring a different feature in a different part of the spectrum, and the two aren't related, they are not chemically or physically related in spectroscopy, you can then go and identify where the iron oxide is. And so the iron oxide, also the iron weight percent from the geochemical analysis are plotted in that second plot. And it shows that the spectroscopy metrics that were derived for this project match very well with the whole rock geochemistry coming out of it. And here we have more hematite equals more ore. So with two straightforward measurements on spectra collected from drill core, we can identify where the ore bearing zones are and where the barren zones are. Now we can also take a look at how the phengite is changing within the heterolithic breccias and the ROXBY Downs granite. So I find this quite interesting. Here's a picture on the left-hand side of 90 meters. And the plot here, the only difference between this plot and the previous ones is that the instead of having the entire column at 300 meters, I broke it up into 100-meter intervals. So it's 0 to 100, 100 to 200, 200 to 300. So we get to see more detail of the drill core, and also it's a little bit of a crisper image as well. So the spectral results, the hyperspectral results are in black here. The whole rock geochemistry, so the aluminum whole rock data are in red, overlaying the hyperspectral data. And then on the right-hand side, you've got this light gray and this dark gray column. These are the fields for high aluminum phengite and low aluminum phengite. So whenever phengite was identified, then there will be a wiggle in either the gray or the light gray or the dark gray, indicating the white mica wavelength position of that particular phengite. So what we see here is there's a lot more detail than the previous figure because it lets us get into this a little bit more detail. And you can see how closely the aluminum whole rock geochemistry data matches up with the spectral data and how much more detail the spectral data provides on the centimeter scale. When we start looking at the phengite trends with high aluminum phengite and low aluminum phengite, you can see that there's actually a huge variation in the composition of the high aluminum phengites within the heterolithic breccias at Olympic Dam. So inside the deposit, it's really chaotic. There's not a lot of stability. It's really, they're very variable in their composition, which is what you saw in that first histogram with the showing the positions of the different wavelengths for those phengites. As you go down, you see most of the, if not all of the phengites are in the high aluminum field. And then when you hit the ROXBY Downs granite, you get your first low aluminum phengite, and it stays that way. There's actually very little variation once you're in the Roxby Downs granite in phengite composition. And when I first started this project, I was kind of told or suggested, it was hoped that I would be looking, the extra 100 meters at the bottom of the drill hole, we were really looking for a trend, like a vector. What can we see in the phengite compositions where they change, and that we can use that to identify another Olympic Dam style deposit. So unfortunately, the phengites are really stable in their compositions this close to the deposit. And I was not able to see any compositional change. That doesn't mean there isn't one. I just didn't see it in that particular project. So, and the reason for that has been explained as I become more experienced, but this question has come up a couple of times as well in other projects and other deposits. And I think the reason you don't see a compositional change in the phengites in the Roxby Downs granite is because this is just too short of a distance away from the deposit. There's a huge amount of water, it's a huge deposit. And so the sericitization of the Roxby Downs granite by Olympic Dam is going to extend, I would say, kilometers into the crustal rocks rather than 100 meters. And so if we're looking for trends, we'd need to be looking at geotechnical holes that extend, hundreds of meters, if not kilometers, into the surrounding areas. Then you'd be able to really kind of take a look at the phengites and see what they're doing. And I believe that from that perspective, probably what would happen is that as you get closer to the deposit, you would be getting more iron-rich phengites, whereas further away you'd have perhaps more magnesium-rich phengites. That's my guess. But I'm not sure if you'd be able to see that in the spectroscopy. It might be something you have to microprobe. So going on from that, we have the role of hyperspectral systems. So when you have a new technology, an emerging technology coming into a field such as geology, they have to define its role, and so that we're not overreaching or extending ourselves with respect to what we can do. But really, hyperspectral systems are very good for exploration. They can help with the search and the identification of alteration minerals that can indicate a nearby hydrothermal event, and there's several examples of this in the literature, and we've done plenty of that work as well. And also something cryptic alteration, which I think is quite interesting, that could indicate a nearby hydrothermal event. And so, for example, perhaps you have a zone of sericitization around Olympic Dam, but beyond that, you'll actually have a zone of cryptic alteration where you won't be changing the composition of the rocks, you'll actually be hydrating them. And so how do you detect that? Very subtle hydration around those hydrothermal deposits, so that if you're drilling in an unknown area, how do you know when you're close to something? You just pull up some granite, or you pull up some other kind of volcanic rock or metamorphic rock. How do you know when you're within an alteration zone or in or a cryptic alteration zone? That's the question. That's where hyperspectral systems are very handy when it comes to drill core logging. Another role is in the mining. So we can use hyperspectral systems to identify ore bearing and problematic units. So here we showed that you can identify the iron oxides, but also the phengite units as well, but also identifying the types of phengites and their abundance. And in the case of some other deposits, we can use an example would be looking at swelling clays. So if you have a swelling clay, this can be very problematic. So you want to be able to identify it, and then you want to be able to quantify how much phengite, swelling clay there is, and so that you can tell the processing people. So what can we do going forward to make mining better? I'd say have a better image at this point, and then to be more sustainable and more accurate, let's say. So we can extract resources better, and there's plenty of companies and people working on that. We just have to start exploring that as well. And then we need to start exploring for resources better. So if you're drilling and you run into you don't hit what you thought you hit, or you didn't hit what you wanted to hit, you need to know what you had there. And sometimes looking at it with the eyes is not the greatest solution. You need other technologies to help out. So one thing we believe is that it's important to automate subjective tasks like logging drill core. There's a lot of evidence that logging drill core is not, with eyes, is not an efficient way to do it. There's lots of inter and intra-observer variability. And so this is a machine that's similar to a TerraSpec. So working on this HYLOGGER project for Olympic Dam, that was for my PhD, came out of that. It made a huge impression on me, and I was like, okay, well, let's take something like this to the field. So the GeoLogger itself is more similar to a TerraSpec that you can move across the surface of the drill core, and it collects hyperspectral data at the rate of 300 spectra per meter. So you get 300 spectra per meter, and it collects high resolution digital photographs. And what it allows you to do is automate subjective tasks like drill core logging. And the reason is not because we want to throw more technology at companies and have them, you know, be intimidated by it, but because actually what happens is you're actually able to produce logs, spectral logs that are incredibly detailed, incredibly sensitive, and really well represent what you're seeing in a deposit. So this is from a project we did with the Northwest Territories, looking at a kimberlite. And this is a kimberlite that's 3 kilometers away from an active mine right now. So it could potentially in the future be placed into the, be mined and processed as well. So what you're seeing here is one of the contrasts. There's a more modern way, I would say, or a more advanced way of processing data rather than using spectral libraries that are provided by software. So when you use TSG or other software packages like that, that rely on linear deconvolution or mineral matching, supported by external spectral libraries, you're really relying on the fact that the spectral library you're using is representative of the rocks that you're analyzing yourself. And most of the times that's not true. And so, for example, if you were to run this data, this hyperspectral data collected from these kimberlites through TSG, it would identify everything as serpentine and perhaps some of the units as saponite. But for most projects, that's not good enough. You can't just say it's a mineral. We need more information from it. And so hyperspectral analyses that hinge on the use of external spectral libraries produce results that are often problematic. And I think this is what can happen when people enter the trough of disillusionment for hyperspectral techniques. And so what we do and the new processing approaches is that they're much more sensitive. So you can identify subtle compositional changes that can be detected with very high precision, allowing for better outcomes. So in general, what we're doing is we're actually extracting a spectral library from your own data set. So if you provide drill core and those drill core are analyzed, we pick out the end members and we build a spectral library from within that, your own data set. And then what you're not doing is you're not comparing it to an external spectral library, you're comparing it to an internal spectral library. And what that means is then you're more able to identify more units and they're more sensitivity. So for example, with kimberlites, being able to identify serpentine is not good enough. You need to identify all of the different kinds of serpentine, and there can be a lot of different kinds of serpentine. And so for example, in these 2 holes, which are like located from this, are pulled from the same deposit, you've got 8 different kinds of kimberlite that are represented by 8 different kinds of serpentine that occur in combination with other clay minerals, such as saponite. And so each color here represents a very distinct mineral or chemical composition that represents a distinct compositional group. And crustal rocks here have all been binned together into purple just to simplify. The customers don't really care about crustal rocks, so just make it purple. But when it comes to kimberlite, they want to know all the details. And so here, each color is a very, very distinct compositional group that may be very similar to something nearby it, but it's still very distinct. And what it allows you to do is identify zones that are unique and then actually correlate with very high accuracy between different drill holes. So going forward, I mean, automation is important. I think this is critical to geology and mining in the future. So automation solves a lot of the 3 problems I talked about in the beginning. The first problem, ore deposits are complex. When we can use machines to collect data and to interpret data, you still need to have them managed by humans, of course, to make sure they're operating properly. But then you're able to attack and understand much more complex things. So you're not relying on a small group of skilled drill core loggers. You're actually relying on data, objective data that can be accurately and validated with other sources. Automation also solves the problem of the skills shortage. So as people leave the workforce and perhaps more people don't come into it, we will need to compensate for that somehow. And then of course, the automation also solves the issue of incorrect drill core logs. So in summary, objective, accurate, precise, and reproducible results that can be produced in a continuously and automated manner can de-risk a project. And in addition, this kind of approach will bring technologically minded people into the field of geology. So perhaps in the future, you'll have geologists that are, able to program in 1 or 2 languages, that they can also, do the heavy lifting and move drill core boxes, but also that they're able to kind of push the field forward and modernize it in many different ways. All right, thank you.
Thanks, Michelle. It was amazing to hear from Olympic Dam and you.
Right, so any questions, then please. I'm not sure how to see them. We'll figure it out.
Yeah. Please, if someone wants to ask to Michelle, please feel free to turn on your microphone, please.
You can say it or you can type it in the chat.
Yeah.
Nothing, anyone?
Well, Michelle, let me check.
How is the spatial, so the question is, how is the spatial resolution within the core? So for the HYLOGGER system, it collects, if I remember correctly, it collects continuously every millimeter, but it bins or it averages a spectrum per centimeter. So for HYLOGGER, there is a spectrum every centimeter that is produced, and that's good. For our system, the one behind me right there, there's a spectrum every 2.5 millimeters.
Michelle, I have a couple of questions.
Go for it, yes.
I saw the spectral data in TSG. What are the invalid mineral groups? Have you done more analysis in your samples?
I'm sorry, I didn't understand. What's the question? Sorry.
What are the invalid mineral group in your?
Yeah. In TSG, you mean?
Yeah.
Yeah, so that just means TSG couldn't see anything. That means that it's another way of saying aspectral. So basically it had no match. And the reason it had no match is because iron oxides don't produce a shortwave infrared spectrum. And so if you have iron oxides, you kind of have just a line like this. And so instead of, when it realizes you don't have any spectral features in it, what it will do is say aspectral, invalid, null. It just gives you an answer saying there's no spectral features there that I can analyze.
Yeah. What kind of breccia was identified at Olympic Dam?
What kind of what?
Breccia?
Volcaniclastic. I'm not sure I understand that question. Yeah, so it's a mixture between the iron ore and between the country rock coming up.
Yeah. We have another question.
Paragonite. Yes. So the question is, you didn't mention paragonite. Have you found any at Olympic Dam? And how does paragonite behave? Did not find any at Olympic Dam. The only time I've seen paragonite is outside of some porphyry copper deposits, but basically it's very distinct in that it goes to shorter wavelengths than muscovite. So it's usually below 2195. There's a, if you've got paragonite, it'll be at 2195. The problem is that if you also have kaolinite, as well, then that also can occur. High crystallinity kaolinite can also produce a spectral feature at that point. So you need to be very clear on what kind of, you can't just make an assessment without taking a look at the rocks. But paragonite is produces a very distinct spectrum compared to muscovite and phengite. And the next question is, in your experience, is it possible to interpret minerals formed by hydrothermal alteration and hydrolysis, such as illite as a form of hydrothermal phyllic alteration? That's a very good question. So in other deposits, you can have multiple episodes of white mica formation, and you can have remnants of, it can be a real basket of white micas, and not just white micas. You get clays, swelling clays, and illites as well. And so what can happen is you can have 14 or 15 different kinds of dioctahedral micas or phyllosilicates in a specific deposit. And then you really have to start looking at what was their first, what was their second, what was their third, fourth, fifth. And so you have this constantly overprinting events. Then, it's important in those situations to really identify what the target is. So it can get overwhelming, but if you know what the target is, for example, a specific kind of muscovite. So you want a high crystallinity, or you want a muscovite that's got a specific coarse crystallinity muscovite, which perhaps is linked to a specific kind of gold deposition. Then you want to go look for that, and you don't need to get bogged down by the rest of the minerals. Or perhaps you're looking for swelling clays, then you need to look for the specifics of those swelling clays. But it is definitely overwhelming to actually realize how many different kinds of dioctahedral phyllosilicates and clays there are in these deposits.
Michelle, I have more questions.
Mm-hmm.
What are the controls of oxidal hydroxyl stretch variation for 3,100 nanometers and 2,290 nanometers?
I don't understand. So what's happening at those wavelengths is what you want to know, or?
Yeah.
So those are the fundamental. Sorry, go on.
The bond, because it's the same stretch, not the same bond, but it's oxidal and hydroxyl.
Yeah.
You
So
mentioned two wavelengths difference for the same bond or oxidal or OH.
So why are they different? Is that the question? So if you have, like, why are the bonds different in muscovite compared to phengite? Is that the question? It's because of the rest of the minerals. So it's actually the bond strength that is making the wavelength change. So if you have a stronger bond strength, so if that mineral is like a harder mineral, that's kind of like, so if your crystal structure is closer together and your bond strength is higher, then you will have a higher higher energy or shorter wavelength at which that bond accepts or absorbs energy. And so if you have more substitution and you have more vacancies, you have longer bond strength, and that is a weaker bond. Okay, there's other questions. Okay. Sorry.
More in the box text.
Okay, so the next one.
John Sharon Sarko.
Yeah, so is there a specific relationship between the different types of white mica and maybe gold, bornite, and chalcopyrite? In some deposits, yes, absolutely. Absolutely. So there are some white micas, white micas, definitely muscovite is a specific type of muscovite is a great indicator of gold or copper in some deposits. But for other deposits, it's like at Olympic Dam, it's a barren zone, right? So you have the ore concentrating in different rock types. but definitely in other deposits, there's definitely white micas and clays that indicate ore minerals. And it might not be exactly there. It might be, there might be a zone of a particular mineral, and then perhaps the copper comes afterwards, right? So it's like kind of, there's these relationships that you need to be aware of between that the minerals, sometimes the ore is not necessarily in the minerals, it just occurs at right after the identification of those minerals. And are there chlorites associated with phengites at Olympic Dam? There are chlorites in the ROXBY Downs granite, there are. And I haven't looked at the microbe data from those, and I haven't analyzed them, but it's very possible that there's some interesting information in there as well. And that could be used as a vector for hydrothermal deposits as well. Chloride is also quite useful. Can I recommend papers on swelling clays and white micas? There's an excellent book called Illites. It's called Illites. It's fantastic, published in 2004. I'm trying to remember who wrote it. I'm just gonna Google that so I can type it in here. It's fantastic. Illites. You'd be like, who would read a book about that? But it's called, I'll just put it in. I wonder if I can type in there too, hey? This book.
Thanks.
Oopsie, sorry, I just, computers, hey? This book, so this link will go to a Springer, it's a Springer book. It's called Illite, Origins, Evolution, and Metamorphism by, I'm not sure how to pronounce his name, Meunier and Velde. Oh boy, that's expensive. But if you need a copy, I have it scanned. Send me an email and I will send you a digital copy of it. So yeah, that's a great book on about how to understand what's going on when it comes to dioctahedral biosilicates.
Thanks, Michelle. We are contacting you. And we have a few questions from Facebook as well, please.
Oh, Facebook. Hi, Facebook.
Yeah. Afternoon, Michelle. Takeshi speaking. We have 3 questions. The first one, I think you already answered, but is it paragonite related to ore zones, like closer to the ore?
It can. In some deposits, it can. Olympic Dam, but not. There's nothing in Olympic Dam, but in because each deposit has its own characteristics, it can absolutely be an indicator for specific deposits. And I have worked on deposits where paragonite is important, but you have to, it's deposit specific and project specific. Yeah.
Okay. Next question is, do you recommend the use of this tool in early greenfield exploration, or is just for more advanced projects?
It
or
depends.
You need more drill hole data?
No, you can do it on 1 or 2 drill holes. It depends though, because it's hard to have the context. So I think in the very early stages, it's best to rely on analytical techniques like, collecting samples, sending them away, getting some thin sections done, getting some whole rock geochemistry, collect some XRF data. Then if you have something really promising there, then it's time to kick it up a notch and start exploring these emerging technologies. I think because at the beginning, most of these exploration projects are run by smaller companies. You don't have a huge budget, and you definitely want to get that fundamental analytical work done before you start trying out emerging technologies. So, but we're definitely involved in early projects, but it's more of a case of I recommend in the beginning, maybe take a TerraSpec out or a Halo, collect some spectra that way. And every meter, collect a spectrum every meter, we'll take a look at that data. If we see something good, like let's say we find some kaolinite, some high crystallinity minerals and some really exciting, indicators, then, well, that's great. And then there'll be a potential to bring in the big guns later. But really the best thing at the beginning of a project would be to do that basic analytical work and then have a TerraSpec if there's money in the budget for it.
Okay, last question, I think from Facebook. Is at Olympic Dam, is there a relationship of aluminum content in phengite and the composition of the host rock?
I'm going to say I don't know, but I also suspect that the aluminum content is changing because of the ore formation. So the phengites that are currently in Olympic Dam that are high aluminum would not have been originally that composition. They would have been the composition of the phengites that are in the ROXBY Downs granites. So something happened to them while they were in this massive deposit that turned them into something else. So they're kind of the next level of alteration beyond kind of the phengites in the ROXBY Downs granite.
Excellent. I have a question. I don't know if you heard the grazing alteration. So it's like,
what is it called?
Grazing. It's like coarse grain muscovite alteration.
Yeah. Yep. I know about that. I didn't know the name, but I know about coarse grain muscovite alteration. Yes.
Sometimes that alteration can be phengitic. So
yes.
The question is if there's like relationship between the 2200 wavelength peak,
yeah,
and the coarse grain and the grain size. Is it coarse with fine grain phengite?
That's a good question. So what we need to do, which I didn't talk about in this talk, but which we do usually, is we also analyze for grain size. So what you get is a diagram that shows white mica wavelength and then crystallinity on the y-axis. And so then what you can do is you don't just have phengite, you actually have, or muscovite, you don't have phengite muscovite, you actually have phengitic compositions of different grain sizes and muscovitic compositions of different grain sizes. And so you can have a coarse grain muscovite, a coarse grain phengite, and then you can have fine grains, then call them, once they hit clay size, then we call them illites. And then you still have these muscovitic illites, these phengitic illites, and then eventually you get to the clays, and perhaps you've got swelling clays or non-swelling clays. And so this is a transitional, I wouldn't say transitional, but this is, in the picture, it's a gradational thing. The actual phase changes to make these minerals is more complicated than a diagram, but in essence, you have a diagram that shows coarse grain minerals at the bottom and really fine grain micas at the top, and then the X and Y really being the X-axis being that white mica wavelength information. So yes, you definitely need to be able to not just separate based on white mica wavelength, you also need to do a crystallinity analysis as well based on the spectra.
Thanks.
So there's another question here. Except for the composition of the major elements and chair mark substitution, have you investigated whether the halogen elements and some trace elements can also cause a wavelength shift? It cannot. It cannot. It is the bond between aluminum and hydroxyl. So I don't think trace elements will affect that shift. But honestly, I haven't done any calculations to test that. As far as I understand, that's a pretty stable bond that is really related to the general structure of the mineral. I'm going to say that trace element and halogen should not affect that white mica wavelength. But obviously, if somebody were to test it and show me, then I would be happy to know. That'd be interesting.
Thanks, Michelle. I think it's the last one.
Okay, great.
Yeah.
All right, thanks a lot.
Thanks for coming to all. It was amazing to hear from you.
Right.
We're waiting for the next meeting.
Yes, exactly. Yeah, that's right.
Yeah.
Okay. Well, thanks for having me. And, obviously, if anybody wants to learn more about this, then contact me and ask questions there as well.
Thanks.
All right.
Thanks, great.
Thanks, everybody. Bye.
Yeah. Thanks.